Welcome to the 13th lecture in general topology. The topics that we will explore in this lecture include properties of the cofinite and cocountable topologies, the order topology on the reals and the rationals, and an introduction to first and second countable spaces. Okay, so we'll start with some exercises from the previous lecture. So let X be a cofinite topological space where the underlying set X is not finite, then the space X is not T2 or Hausdorff. So proof. Let X and Y be 2 points in the space X such that X is not equal to Y, so 2 distinct points in the space. Then for every open neighborhood U of X, the complement of that neighborhood is finite. Similarly, for every open neighborhood V of the point Y, the complement of that neighborhood is finite. And so the union of the complements, which is the same as the complement of the intersection of the neighborhoods U and V, is finite, since finite unions of finite sets are finite. And hence the intersection of the open neighborhoods U and V is cofinite. Further, as the underlying set is not finite, this cofinite set, which is the intersection of the neighborhoods U and V, contains infinitely many points of the underlying set X. And in particular, this intersection is not empty, and this is true for every open neighborhood U of X and every open neighborhood V of Y, and therefore the space X is not T2 or Hausdorff. Okay, next. Once again, let X be a cofinite topological space where the underlying set is not finite, then every finite set F, which is necessarily a proper subset of the space X, is nowhere dense. In the space X. So proof. As the space is T1 or Frechet, every finite point set is closed And so the closure of the finite set F is the finite set F. Now, as the underlying set is not finite, every non-empty open set contains infinitely many points of the underlying set X. And so the interior of the finite set F is empty. And hence the interior of the closure of the finite set F is the interior of the finite set F, which is empty. And therefore, the finite set F is nowhere dense. In the space X. All right. Next, let the collection tau be the set of all subsets U of the set X, where either U is empty or the complement is countable. Then this collection tau is a topology on the set X. And once again, this topology is called the cocountable topology. So proof. First condition of the definition, clearly the empty set is in the collection tau. And since the complement of the entire set is the empty set, which is countable, the entire set is in the collection tau. So second condition, let the set of sets U sub I for I in some indexing set I be an indexed family of non-empty sets in the collection tau. Then the complement of the set U sub I is countable for every index I in the indexing set I. And so the arbitrary intersection of the complements of the sets U sub I, which is the same as the complement of the arbitrary union of the sets U sub I, is countable, since arbitrary intersections of countable sets are countable. And hence the arbitrary union of the sets U sub I is once again in the collection tau. Now clearly, the union of the empty set with this arbitrary union of non-empty sets in the collection tau is also in the collection tau, and thus arbitrary unions of sets in the collection tau are also in the collection tau. So the second condition is satisfied. So now we look at the third. Let U sub 1 through use of n be non-empty sets in the collection tau, then the complement of the sets u sub I is countable, and this is true for every index I in the finite set of consecutive integers from 1 to n. And so the finite union of the complements, which is the same as the complement of the finite intersection of the sets u sub I, is countable. Since countable unions of countable sets are countable, and hence the countable intersection of non-empty sets in the collection tau is once again in the collection tau. Now clearly, the intersection of the empty set with this countable or finite intersection of non-empty sets, which is the empty set, is once again in the collection tau, and thus finite intersections of sets in the collection tau are also in the collection tau. So all three conditions of the definition for a topology is satisfied, and therefore the collection tau is a topology on the set X. Okay, so next we will show that every cocountable topological space X is T1 or Fréchet. So proof. Let X be a point in the space X. Then since the complement of the singleton containing the point X is the singleton containing the point X, and this is a countable set, we have that the complement of the singleton is open, and so the singleton itself is closed, and we chose the point X arbitrarily, and hence every singleton is closed. And therefore the space is T1 or Fréchet. So let X be a cocountable topological space where the underlying set is not countable. Then the space X is not T2 or Hausdorff. So proof. Let X and Y be 2 points in the space X. that are distinct. Then, for every open neighborhood, U of the point X, the complement of that neighborhood is countable. Similarly, for every open neighborhood, V of the point Y, the complement of that neighborhood is countable. And so the union of these complements, which is the complement of the intersection of these neighborhoods, is countable, since countable unions of countable sets are countable. And hence the intersection of the neighborhoods U and V is cocountable. Further, as the underlying set is not countable, this cocountable set, which is the intersection of the neighborhoods U and V, contains uncountably many elements of the underlying set X. In particular, the intersection of U and V is not empty, and this is true for every open neighborhood U of X and every open neighborhood V of Y, and therefore the space is not T2 or Hausdorff. Okay, so let X be a cocountable topological space where the underlying set is not countable. Then every countable set C, which is necessarily a proper subset of the space X, is nowhere dense in space X. So proof, as the countable set C is the complement of itself, the set C is closed as its complement is open. And so the closure of the countable set is the countable set. And as the underlying set is not countable, every non-empty open set contains uncountably many elements of the set X. And so the interior of the countable set is the empty set. And hence the interior of the closure of the countable set is the interior of the countable set, which is empty, and therefore the countable set C is nowhere dense in the space X.